Okay, we'll make a start. Welcome everybody to Astronomy Education. My name's Colin Hill, and tonight I'll be talking about great discoveries in astronomy. So tonight I'll be taking you through a journey through time, starting in ancient Greece, moving through to the modern age, and stopping at certain places to look at great discoveries in astronomy along the way. But first, we acknowledge and pay our respects to the Gawler people, the traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and relationship of the Gawler people to country, and we respect and value their past, present, and ongoing connection to the land and cultural beliefs. Right, so I said we're going to start in ancient Greece. So crystal spheres, this wasn't so much a discovery because they never really existed. But it's more of what they believed in at the time. And this sort of sets the scene for the next 2,000 years or so. So they were very competent mathematicians, and they believed that there were crystal spheres rotating around the Earth. So the Earth was at the centre here. And all of the objects in the night sky were attached to crystal spheres. So the moon was the closest one. They realised that. So it was on its own little sphere. And then Mercury and Venus, they knew that they were closer to us than the sun. But then the sun had its own sphere here, and then the other planets out to Saturn, because at that time, Saturn was the furthest planet that they knew existed. And beyond that was the sphere of the fixed stars. And then beyond that was the sphere of the prime mover, which sort of held it all together, I imagine. And, this was sort of come about because of just observation. That, we felt like the Earth was at the centre, and when we looked up, everything seemed to revolve around the Earth. So it was sort of, logical at the time. Now, Aristotle, he modified the theory because there was a problem with this. Some of the planets at certain times of the year appear to stop and then go backwards and in retrograde motion. And they couldn't really account for that if they were on a fixed sphere revolving around the Earth, because the sphere wouldn't just stop and then move back the other way. So he added more spheres called epicycles. So here we had the sphere of the planet, and there was another little sphere here that accounted for the planet going back the other way during its orbit. Obviously, the planets don't stop and go back the other way. It's just because of our point of view in our orbit. As we overtake an outer planet, it appears to stop and move back the other way for a period of time. But they didn't realise that at the time. So Aristotle introduced these epicycles to sort of take that into account. But it started to get very complex, as you can imagine, and ended up with 56 spheres in all at some point. And Ptolemy also embraced the epicycles in his great book, the Almagest, in 150 AD. So you can see this idea lasted for a very long time. Now, Pythagoras, he was believed to be the first person to reason that the Earth was spherical. So back then, the sphere was regarded as a perfect geometric shape. So he reasoned that the Earth was a sphere because that's the most perfect geometric shape. But he had no proof of that. And it wasn't until Aristotle, about 150 years later, who observed the Earth's shadow on the moon during a lunar eclipse, that he found direct proof that the Earth was actually a sphere or circular. And Pythagoras, he also realised that the orbit of the moon was inclined to the Earth's equator, and that Venus was both the evening and the morning star, because prior to that, it was believed that they were actually separate objects, I think. So this is the same guy that came up with Pythagoras' theorem. So he was also a mathematician. Then we come to Aristarchus of Samos, and so he came up with an idea of how to work out the relative distance of the moon and the sun using geometry. So he basically came up with this idea. So when you've got the first quarter moon, so he realised that you would get a right-angled triangle from the sun to the moon to the Earth. So he realised if he could measure that angle there, he could work out the relative distance of the moon and the sun, not the absolute distance, but the relative distance. Unfortunately, his measurements weren't very good because this angle here, he measured it at 87 degrees, but in fact it's 89 degrees and 51 minutes. So it's almost a right angle because that distance there is a much longer than this distance here. So this angle here is approaching is 90 degrees. So his measurements weren't very good. So he believed that the sun was 19 times further away or larger than the moon, where in actual fact it's 400 times. But his geometry, his theory was correct. Then we come to Eratosthenes. I have trouble with these names. Now he was very clever. He estimated the circumference of the Earth by measuring angular displacement of the sun from zenith at two locations. So obviously he did this at the same time in consecutive years. So he went to Syene, which is here, and at noon, the sun was virtually directly overhead. So you end up with a 90-degree angle here, right? And then a year later, I think he went to Alexandria and did the same thing at noon, and he found that the angle was 83 degrees, so which was 7 degrees off the zenith. And by knowing the distance between the two cities and knowing that angle, he worked out the circumference of the Earth. Unfortunately, the units he used were stadia, which is the size of a stadium, because we don't really exactly know exactly how big a stadium is. It's unsure how accurate his measurement was, but it was a very clever way of determining the circumference of the Earth back in those days. Then we come to Hipparchus. Now he was a very clever man. He constructed the first accurate catalogue of stars, of star positions, and he was inspired after he witnessed a supernova. So he did this all with just very simple instruments and naked eye observing. And his observations led to one of the most serious challenges of Aristotle's view of the cosmos, because he noticed that the celestial sphere precessed or shifted over time. And before that, everyone thought that the stars were fixed and never moved in the night sky. But he actually found that they do slightly move over time. And he did this by comparing the star positions that he measured with previously logged star positions by the Babylonians about 200 years prior. And using the Babylonian star positions, he also measured the length of the year to within 7 minutes, which is quite remarkable for the time. Now, he also developed the basis of the magnitude system, which we use today. So because he didn't have a telescope, he could see the brightest star he said was magnitude 1, and the faintest star he could see, he called it magnitude 6. So that's the basic system which we use today. But obviously we've got objects that are brighter than the brightest star, like some of the planets and the moon and the sun. So they have magnitudes less than 1 or going into the negatives. And obviously because we've got telescopes, we can see stars much fainter than magnitude 6. And we now have a mathematical basis for the magnitude system. So it's, I think, fifth root of 100, I think, is 1 magnitude. That's the basis we use. It's about 2.5 times each magnitude. Now you can see there's a big leap in time here. So we've sort of gone from from 150 BC to the 1400s. So this is because of in Europe, this was the Dark Ages, and not a lot of astronomy happened in that time. Though apparently the Arabs or the Islamic parts of the world still actively pursued astronomy during this time. So Nicholas Copernicus, so he developed the heliocentric model of the solar system that finally overturned Greek astronomy. So you can see it lasted for a couple of thousand years, the idea that the Earth was at the centre of everything. So he worked out that the Earth revolved around the sun. He said that the distance from the Earth to the sun is imperceptible compared with the distance to the stars. And the rotation of the Earth accounts for the apparent rotation of the stars. The apparent annual cycle of movements of the sun is caused by the Earth revolving around the sun. And that the apparent retrograde motion of the planets is caused by the motion of the Earth in which one observes those planets. Now, he put all this in a book, the De Revolutionibus, which is basically the revolution of the planets. But he was very loath to publish this book because he feared ridicule from the scientific community. So even though his friends urged him to publish it, he did not until he was on his deathbed. And I think it got published about 2 days before he actually died. Then along came Galileo Galilei about 100 years later. So also a very clever man. He was the first person to use a telescope for astronomical observations. So he didn't actually invent the telescope, but he improved on the design and was the first to actually point it at the sky. It's amazing he saw anything at all because the telescope had an aperture of about 2.5 centimetres, and people who have looked through replicas say it's like looking through a drinking straw. So it's amazing he saw anything at all. But using these telescopes, he made some profound discoveries like craters and mountains on the moon. He saw the 4 big Galilean satellites around Jupiter. And when he put it onto Saturn, because the telescope wasn't very good, he couldn't resolve the rings. He just saw them as appendages, and he could never work out exactly what they were. It wasn't until about 60 years later that I think Cassini worked out that they're actually a ring around the planet and not appendages. He also discovered that the Milky Way was made of individual stars. Before that, it just looked like a cloud in the sky. And he also saw sunspots on the sun, which was probably a bad thing because it damaged his eyes in the process. Now, he upset the Catholic Church, obviously, by opposing the Earth-centered doctrine, and he was found guilty of supporting the Copernican model of the solar system by the Inquisition. And but because he was such a famous person, rather than being imprisoned or sentenced to death, he was sentenced to house arrest for the rest of his life. Then we come up to Johannes Kepler. Now, he was an assistant to the great astronomer Tycho Brahe. And when Tycho died, Kepler inherited all his precise astronomical observations. And using this data, he was able to explain in detail the planetary motion and predicted the transits of Venus and Mercury. And he developed the 3 laws of planetary motion. Because before that, it was assumed that the planets orbited the sun in circular orbits. But he realised that they move in ellipses. And the planets move in such a way that a line between the sun and the planet sweeps out the same area in the same time, no matter where in the orbit. So it doesn't matter where they are in the orbit, If that time is the same as this time and this time, then this area under the curve is the same. He also, law 3 states that the square of the period of the orbit of the planet is proportional to the mean distance from the sun, cubed. So P is period squared is proportional to distance cubed. So it basically means the further out you get from the sun, the slower the planets move. Then we come to Sir Isaac Newton, so one of probably the greatest scientists of all time. So he developed the 3 laws of gravitation. So the laws are a moving object will continue in a straight line unless acted upon by a force, e.g. gravity. An object will accelerate in the direction the force is acting upon it. And if an object is pushed or pulled, it will push or pull equally in the opposite direction. He also invented the Newtonian telescope. So prior to that, all telescopes were refractors and had lenses. So he was the first to use a mirror, and then a secondary mirror here, and putting an eyepiece here. Unfortunately, back then they didn't have aluminized glass as a mirror, so they had to use a metal called speculum. It was an alloy. I'm not quite sure what metals were in the alloy, but it tended to tarnish very, very rapidly. So they were forever polishing the mirrors back then when they were made of speculum metal. He also discovered that white light could be broken down into a spectrum using a prism. So next month, I'll be giving a talk on gravity as well, and I'll be covering Sir Isaac Newton in a bit more detail in that. So then we come to William Herschel. So we're getting into about the 1800s now. So he built the biggest and best telescopes of the time, including this huge one here. It was 40 feet long and had a 50-inch mirror. It was a Newtonian. And even though it was very impressive, it was a bit cumbersome to use, as you can imagine. But he discovered the planet Uranus and its 2 of its moons, Titania and Oberon. And his sister Caroline, who's under there, she herself discovered 8 comets in her own right. So when that Uranus was first discovered, it was sort of called Georgius Sidus after King George, and then later named after William Herschel himself, Herschel. But later, trying to keep in, with the naming of the other planets, they changed it to Uranus, which is one of the gods. Can't remember what he's the god of. Then we come to Adams and Leverrier. I'm not sure, I didn't put the dates there, but oh, here we go, 1845. So this was one of the triumphs of mathematical astronomy. These 2 guys independently calculated the position of a new planet because they noticed that the orbit of Uranus was being perturbed by something further out, gravitationally tugging on it. So they calculated the position of a new planet. Now, using this information, a German astronomer, Johann Gottfried Gawler, observed the planet a year later in 1846 within a degree of the predicted position. So that was quite a triumph of mathematical astronomy. So then we come into the 20th century. And at that time, early in the 20th century, everybody believed that the Milky Way galaxy was the entire universe, basically. That's all there was. They could see distant galaxies, but they believed that they were nebulae within the Milky Way. They weren't external systems. So in 1924, Edwin Hubble proved the existence of large star systems or galaxies far outside the Milky Way. And he identified a relationship between a galaxy's distance and its speed of recession, which is known as Hubble's law, because he worked out that nearly every galaxy he observed was moving away from us, except for a few in the local group. He also developed a method for classifying galaxies, which is often called the tuning fork diagram because of its shape. So here we have the elliptical galaxies going from spherical to elliptical, and then the transitional galaxies, which are halfway between a spiral and an elliptical. And then we have the spirals, with the classical spirals and the barred spirals. Then we come to the 1930s, and Clyde Tombaugh, he was tasked with searching for planet X. They believed that there was another planet out past Neptune, and the position of this planet was predicted by Percival Lowell and William Pickering. So he started to do sweeps of the area where these astronomers predicted this planet should be. And he used a blink comparator. So we would take images over a series of nights and then run them like a little movie, and the stars would stay still, but any planet would move from night to night. And using this method, he discovered Pluto. So everybody thought, well, we've found planet X. But it wasn't long before they realised that it was very, very small, and it probably wasn't the planet that they were looking for as predicted by Percival and William. But it became quite a profound discovery at the time. And he also discovered hundreds of asteroids while searching for Pluto. So as it turns out, Pluto is just one of the largest members of the Kuiper belt of asteroids. Then we come to the 1960s. So Jocelyn Bell, who's still alive, discovered pulsars in 1967 while she was working on her PhD. And she's actually given a talk to our society about 20 years ago, I think, when we were in the Kerr grant. She actually came and did a talk for us. And while she was working on the radio telescope, she noticed a regular signal in the data stream coming through, and it was on a chart recorder, and she called it a little bit of scruff, I think was the terminology they used. And at the time, they thought they might have found evidence of an alien civilization, and the signals were dubbed LGMs for little green men. But it wasn't long before they realised that they were actually coming from rapidly rotating neutron stars or pulsars, because these stars rotate extremely rapidly, hundreds of times a second, and they're putting out beams of radio waves from the magnetic poles. And if Earth happened to be in the path of these beams, we'd see a very regular radio signal being emitted and received on the Earth. So she was the first to discover pulsars. Now, black holes. So black holes were actually hypothesized in the 18th century, but they called them dark stars back then, because they worked out then that if you could compress a star to a certain diameter, then its gravity would be so great that it would exceed the escape velocity of light and would effectively disappear. So they actually worked it out back in the 18th century. And that they were later predicted mathematically by Einstein in his theory of relativity. The direct evidence for black holes didn't come until 1971. with X-ray emissions from a binary star system called Cygnus X1. So Cygnus X1 is a binary system. So the primary star is a blue giant, and the secondary star, which they couldn't see, but they knew it was there because they could see the primary star being tugged back and forward by a massive object which was several times the mass of the sun, but they could not see it. There was no spectrum from it, but there are lots of X-rays coming from the system. So what they believe is happening is that the orbit is very, very tight, and the gravity of the black hole was sucking gas, hydrogen gas off the giant star, and it was going into an accretion disk around the black hole and then spiraling in. And as it spiraled in, it got very, very, it spiraled very, very fast. It spun, as it was spiraling in, it was spinning around very, very quickly and heating up to millions of degrees. This generated the X-rays that they were observing. So it was sort of indirect evidence of a black hole because it was the only object that would match the observations they were getting. Okay, dark energy. So this is a force of unknown nature which is causing the universe expansion to accelerate. So prior to the 1990s, everybody knew the universe was expanding, but they believed that it was expanding at a fixed rate and would probably, if anything, slow down over time due to gravity. But the Super Cosmology Project and the High Z Supernova Search Team, while looking at very distant Type 1a supernova, noticed that these supernova were fainter than they should be. Because Type 1a supernova are treated as standard candles because they have exactly the same mechanism that triggers the explosion. So most Type 1a supernova are intrinsically the same brightness. So they use them as standard candles to work out distances. But they were noticing that a very distant Type 1a supernovae were fainter than they should be because they were further away than they should be. And this is because the universe's expansion is accelerating, and it's accelerating due to dark energy. But we don't know what dark energy is, but it makes up 70% of the mass energy content of the universe. So it acts like an anti-gravity force, and its effect is increasing with time. And it's defined by the cosmological constant, that's lambda. So this is a term in Einstein's field equations. He originally put it in the equations to stop the universe from expanding. Because when he came up with the general theory of relativity, he was amazed that the equations showed that the universe was expanding. Because back then they thought it was static. You know, it was exactly the same as it's always been and never changed. So he put a term into his field equations to produce a static universe. When he found out that the universe was expanding, he realised his mistake and took the term out of his equations. But it turns out that they've had to put that term back into the equations because of dark energy. However, I think the value was negative and not positive like Einstein had it. And this pie chart here shows the makeup of the universe. So it's 75% dark energy, which we don't know what it is. It's 21% dark matter, which we don't know what it is, and 4% normal matter, which we do know what it is. Pretty depressing, isn't it? Then we come to gravity waves. So this is only in the last 10 years or so. Prior to that, they were predicted. General relativity predicted gravity waves. But back then, they thought that they would be so small and so weak that we'd never, ever be able to detect them. But detect them we have. And we use the LIGO detectors. So this is the LIGO detector. And it is huge. See, these tunnels are 4 kilometres long. And if a gravity wave travels through the Earth, it actually compresses space-time very so slightly as the wave goes through the Earth. So, everything sort of compresses and just a little bit. So that's what we have to try and detect, is these compressions of a gravity wave, but not detecting anything else that may cause ripples as well, like somebody driving a truck past the observatory or the detector. So they used a right angle detector. So it had a laser here, and it would go through to a beam splitter, which would split it into 2 beams, one beam going up this tunnel and the other beam going down this tunnel. We go through these partially reflective mirrors and then to a fully reflective mirror and then bounce back again, back to the beam splitter where it was recombined with the other beam and then to a light detector. So normally, if there was no wave going through, the 2 beams would be out of phase. But if a gravity wave went through the detector, it would compress the distance ever so slightly in one leg more than the other leg. So you would get a phase shift or an interference pattern generated. So this is the basis of how they did it. But the amplitude of a gravity wave going through the Earth is smaller than the diameter of a proton. So that's why they thought it would be impossible to detect it. But they have done it on many occasions now. And they've got 2 of these detectors, a few thousand kilometres apart. So when a gravity wave goes through the Earth, gravity waves travel at the speed of light. It hits one detector before the second detector. So they'll see the same event in both detectors, but with a slight delay. So that's how they can determine that it's not a localised event, that it is actually a gravity wave. Now, gravity waves themselves, anything that accelerates generates gravity waves. Even if you just wave your arm in the air, you're generating gravity waves, but they'd be so small that you'd never notice them. The only way we can detect them at all is through catastrophic events in the universe, like colliding black holes. So if you've got 2 black holes that are in orbit around each other, they slowly spiral into each other because they're radiating gravitational energy and their orbits decay. And as they go into their death throes just before they merge, they're whipping around each other at a sizable fraction of the speed of light. And so they're accelerating, because of the orbit, they're accelerating, and it's generating these gravity waves out into space. And then when they actually merge, they get a chirp, like a spike in the gravity waves, and then nothing. And that's exactly what they've detected in these detectors. That gets us to the present. Any questions? I've always rely on you for a question, Peter, can't I? Yeah. Sorry? I think there is a project to do that. Yeah. I can't remember the LISA. I think it's called LISA. I don't remember what it stands for. They always come up with a name and then work out the words for it later. But I think, I'm not sure if it's ever going to go ahead, but yes, they're like big mirrors in space. And I think the beauty of being in space, they can get a long way apart, and there's no terrestrial interference at all. But they can actually get they can actually measure colliding neutron stars as well, down to that sort of level. But these are like events that are billions of light years away, these collisions. So these gravity waves have been spreading out through space for billions of years before they hit the Earth. Yeah. Any other questions? All right, well, thank you very much.